Imagine harnessing the entire energy output of a star. This is the idea behind a Dyson Sphere. Sounds like something straight out of a science fiction novel, right? But it's actually a concept proposed by physicist Freeman Dyson in the mid-20th century. The Dyson Sphere is a hypothetical megastructure that completely surrounds a star, capturing a significant percentage of its power output. The energy harnessed could theoretically solve any power demand of any civilization, making it a concept that's hard to ignore. Dyson's idea, while seemingly far-fetched, is rooted in the concept of a Kardashev scale, a method of measuring a civilization's level of technological advancement based on the amount of energy they are able to utilize. A civilization capable of harnessing the energy of an entire star would rank highly on this scale, indicating an advanced level of technological prowess. Now, how does one go about building such a gargantuan structure? Let's delve into it. Building a Dyson Sphere is an immense task, needing incomprehensible amounts of material. Imagine, if you will, the colossal endeavor of constructing an artificial shell around a star. The sheer scale of it boggles the mind. But let's break it down to its core elements, the building blocks, if you will. Firstly, we need a material that can withstand the intense heat and radiation of a star, as well as the cold vacuum of space. Now, you might think of steel or concrete, but these conventional materials are far from adequate. They would simply melt or disintegrate under such extreme conditions. Instead, we'd need to turn to advanced materials, things that are still largely theoretical today. Materials like carbon nanotubes or graphene, which are known for their exceptional strength and heat resistance. Secondly, we need to consider the sheer volume of material required. To give you a sense of scale, if we were to build a Dyson Sphere around our sun, with a thickness of just 1 meter, we'd need roughly the equivalent of all the matter in our solar system, excluding the sun itself. That's right, we're talking about Jupiter, Saturn, Earth, and all the other planets, moons, asteroids, and comets combined. Lastly, we need to consider the issue of energy. Building a Dyson Sphere would require an astronomical amount of power, not only for the construction itself, but also for maintaining the structure once it's in place. This energy could potentially come from the star itself, but harnessing that power is another challenge altogether. So, to sum it up, building a Dyson Sphere would require advanced materials beyond our current technological reach, a virtually limitless supply of matter, and a staggering amount of energy. You might say it's a project of stellar proportions. The next question is, where will we get such an enormous amount of material? The answer is right here in our solar system. The vision of constructing a Dyson Sphere, a megastructure encompassing a star to harness its energy, requires vast quantities of materials. But where can we find such a colossal supply? The solution lies in our cosmic backyard. Let's start with the asteroid belt. Located between Mars and Jupiter, it's a veritable treasure trove of metals and minerals. Some of these space rocks are primarily composed of nickel and iron, while others are rich in precious metals like platinum and gold. Even a single mid-sized asteroid could contain more platinum than has ever been mined on Earth. But asteroids are just the beginning. The moons and planets of our solar system also hold a bounty of resources. Take, for instance, the moon. Lacking an atmosphere and a magnetic field, the lunar surface has been bombarded by asteroids for billions of years, leading to a rich deposit of helium-3, a potential fuel source for nuclear fusion. Then there's Mars, with its vast reserves of iron, titanium, and nickel. Even its regolith, the layer of loose, fragmented material covering solid bedrock, can be used to produce bricks for construction. And what about the gas giants? Jupiter and Saturn are huge reservoirs of helium and hydrogen, essential ingredients for fusion power. But the real jackpot might be the icy moons of the outer planets. Europa, one of Jupiter's largest moons, and Enceladus, a moon of Saturn, are believed to harbor vast oceans beneath their icy surfaces. These oceans could provide the water needed for life support and fuel production. So, you see, our solar system is not just a collection of celestial bodies orbiting a common star. It's a vast, untapped vault of resources waiting to be unlocked. The potential of mining the solar system is not just about the Dyson Sphere, it's about the future of humanity. It's about transforming us into a truly spacefaring civilization. Now that we have the materials, the next challenge is how to assemble them. Assembling a Dyson Sphere would be the greatest construction project humanity has ever undertaken. Imagine, if you will, constructing a colossal structure encircling an entire star. The scale is mind-boggling and the challenges are immense. But let's break it down. First, we must consider the method of construction. One possible approach could be using autonomous, self-replicating machines, much like 3D printers. These machines, referred to as von Neumann probes, would mine resources from the solar system, replicate themselves, and start the construction process. Over time, these probes would build up the Dyson Sphere, piece by piece, like the world's most ambitious jigsaw puzzle. But what about the challenges? Well, there are plenty. For starters, the sheer scale of the project is daunting. A Dyson Sphere would have a surface area of about 600 million times that of Earth. That's a lot of real estate to cover. And then there is the issue of managing the colossal amount of energy produced by the star. We'd need to develop materials and systems capable of withstanding and managing the heat and radiation on a scale we've never before contemplated. How could these challenges be overcome? Well, that's where advances in technology and our understanding of the universe come in. We could harness the power of quantum computing and artificial intelligence to design and control the von Neumann probes. We could also develop new materials, using nanotechnology and exotic states of matter, to build a structure capable of withstanding the harsh conditions inside a Dyson Sphere. But let's not forget, this would be a multi-generational project. It would take thousands, if not millions of years to complete. And along the way, we would need to develop a sustainable way of living, not just for us, but for the countless generations that would call the Dyson Sphere home. Once completed, we would have a superstructure capable of harnessing the energy of an entire star. But when will we be able to build one? Building a Dyson Sphere is not something we can do with our current technology. That's a bit of a bummer, isn't it? But don't get disheartened. We're going to break down the advancements we need, the timeline for those advancements, and when we could realistically expect to build a Dyson Sphere. Firstly, let's consider the sheer amount of material needed. We'd need to mine not just our Earth, but potentially our entire solar system to gather the resources. This means we'd need autonomous robots capable of interplanetary and asteroid mining. While we have made strides in robotics and space exploration, achieving this level of resource extraction is likely a couple of centuries away. Next, we need to think about how to assemble this colossal structure in space. We're talking about an engineering feat on a scale we've never even come close to before. We would need to develop construction techniques that work in the vacuum and zero gravity of space. This would not only involve advancements in robotics and AI, but also improvements in materials science. The timeline for this, it's hard to say, but optimistically, we might be looking at another few centuries. The final piece of the puzzle is energy. A Dyson Sphere is all about harnessing the power of a star. We've made some progress in understanding and harnessing nuclear fusion here on Earth, but we're a long way off from being able to control the power of a star. Again, we're probably looking at a timeline of centuries. And let's not forget the societal and organizational challenges. Coordinating a project of this magnitude would require an unprecedented level of global cooperation and resource allocation. It's a huge if, but if we can overcome these hurdles, we might just be able to build a Dyson Sphere in the next 1,000 years or so. So, in the grand scheme of things, we're at the very early stages of this journey. We're making progress, but there's a long, long road ahead. So how close are we to building a Dyson Sphere? Well, we've still got a ways to go, but who knows what the future may hold. The idea of a Dyson Sphere is still largely theoretical, but we are making strides towards such megastructures. Today, scientists around the globe are exploring the feasibility of this colossal energy harvester. Theoretical physicists and engineers are studying the mechanics, materials, and methods that could potentially build this star-hugging structure. In the realm of research, we've seen advancements in space-based solar power, materials science, and astronomical observation techniques. These are crucial steps that are inching us closer to the realization of a Dyson Sphere. However, it's important to remember that we're still in the early stages of this journey. The leap from theory to reality is vast and filled with challenges. The scale of the project is unprecedented, and the technological requirements are immense. While we may not see a Dyson Sphere in our lifetime, the dream of harnessing the power of an entire star is closer than ever before.